about shifting operators. So I need to talk about shifting operators. Okay, so so this is an analog of, this is the algebraic, shifting is the algebraic incarnation of suspension in topology. So motto is that shifting is the algebraic incarnation of suspension in topology. So recall that if so if we had a topological space, right, X, right, then the suspension of X was this thing where we took cones over. So this was the suspension of X, and this is the suspension. Okay, and so like the suspension of the circle is the sphere. Okay, and we wrote it by sigma of X, and it had the nice property that on homotopy, right? So we had pi I of sigma of X of the suspension of X. So this was pi I minus 1 of X. Okay, and HI, so if I did reduced homology, so again, this is H reduced homology of X. Okay, so it shifts, right? Suspension shifts homology. Homotopy groups and homology groups. Okay, so so what is shifting? Okay, so so given a complex of R modules, A. Okay, so A is AN. Okay, then A, let's say AR, so is the complex just shifted to the left. R times. Okay, so let's do the homology version of this first. And then there's like a cohomology version. So for homology, we'll have a complex that's like A0, A1, A2, A3, and so on. Okay, so that's our usual complex A. Okay, so this is degree 0, so maybe we wanted to go to A minus 1. Okay, so this is in degree 0. So now let's shift everything to the left. So A minus 1, so this bumps over. So you have A minus 2. So this is A0, this is A1, this is A2. Okay, so this thing here, this is A1, 0. This is A1 minus 1. This is A1, 1. This is A1, 2. This is A1, 3. Okay, so the thing is that this is like the same complex, and this part here sits in degrees. Sorry, this part here sits in degree 0 now. This term. Okay, so it's important what component they sit in. This continues. Okay, so the formula that we get for this is that A1 of I is A of I minus 1. Okay? All right. For cohomology, you can figure something similar, cohomology. Okay, so let's take a cochain complex. So if we do a cochain complex, so we'll have something like A0 to A1 to A2. So it just is just a difference in numbering. But it's kind of confusing because a lot of people do different conventions, right? And so I just wanted to be really clear about this. Okay, and so now let's shift everything to the left. So this is A2. Okay, this is A3. This is A4, A1, A0. It keeps going. Okay, and so let's make sure that we have the correct degrees. So this is degree 0. This is degree 1. This is degree 2. This is degree 3. Right, this is degree -1. Okay, and so the formula here for shifting is that A1I is A, sorry, this is, these should be uppers. So this is 0, 1, 2, 3, -1. Okay, so this thing here, if I take the ith piece, so you get bumped up. So the 0th piece is now what was the 1 piece. Okay, so this one gets shifted, this one you subtract, and this one you add. Okay, and so let's just check that this is compatible. Is this compatible? With the convention that AI is equal to B minus I. So this is like this is the chain cochain conversion. Okay, so let's define. Okay, so let's define B tilde like so to be equal to by B tilde minus I is equal to A1I. Okay. And okay, and so we're going to use this formula too as well. Okay, so let's check. So A1I. So this is B tilde minus I. And so this is B1 minus I believe. Oh, let's see. So this is okay, so we defined this B tilde to be this. So this is B minus I. Okay, so let's break this down. So this is A of I plus 1 here. And this is B of minus I plus 1. Okay, and so this is B of minus I minus 1. Okay, so let me just get rid of this. So we know that this is B1 and then minus I, because so we subtract, right? So yeah, subtract. So this is B minus I minus 1. Okay, so okay, so in the B tilde, that's B tilde minus 1. So yeah, so great. So it is compatible, right? So if you do this, so if A is defined to be, if you have this thing, then A1 I is equal to B1 1 minus I. Okay, so with these conventions, it's compatible. You just need to shift on the left. Okay, so so it doesn't matter if you shift on the left in homology or cohomology. It's just always just shifting to the left. Okay. So, so what is the effect of shifting on homology and cohomology? So we want something like these formulas here, right? So where suspension has the effect of shifting homology and cohomology. Okay, and so you can see here, so if we were going to compute the zeroth homology here, right, you'd actually be computing the first homology, right? So, or sorry, let's see, the zeroth, so this is degree 0. So or let's say, I guess this is like the first homology. So the first homology in the shifted complex is like the zeroth homology in the original complex. Okay, so let's just make sure that this makes sense. So hi of A1 is equal to hi minus 1 of A. Okay, so let's see if this makes sense. So we saw that the zeroth homology, or the first homology of A1, for example, was equal to the zeroth homology of A. Okay, so this is what we computed by the example. And so if I is equal to 1, this makes sense. Okay, so this formula, this is the formula that you get. Okay. All right, and so for cohomology, what happens? So you shift up, right? So hi. So if we have a chain complex, A1, so this is H of I plus 1 of A. Okay, so let's check again. So let's do the zeroth homology of, so like here, so in degree 0, in the shifted complex, you go to, it's like it's in degree 1, right? So it goes up 1. Okay, so this is the formula here. So shifting shifts the homology. Okay, just like suspension shifts homotopy. Okay. All right. All right. So I need to do double complexes and total complexes. And then I need to do tensor products of chain complexes and mapping cones. And so the idea is that we're going to use this kind of mapping cone property to show that the tors are the same. So okay, so I'm gonna stop here, and then I'm gonna do that next time.